Hi everyone, in this video we will solve problem 5.8 from the book McConkey and Td Eastop, Thermodynamics. So the statement of the problem 5.8 is in a dual combustion cycle, the maximum temperature is 2000 centigrade and the maximum pressure is 70 bar. So to calculate the efficiency and the mean effective pressures when the pressures and temperatures at the start of the compressors are 1 bar and 17 centigrade respectively, and the compression ratio that is given is 18/1. Okay, so before solving this problem, I have shown the dual combustion cycle on the right side. So you here in dual combustion mean that the combustion takes place at a constant volume as well as at a constant pressure. So the total heat that is supplied will be the sum of the heat that is supplied in process 2 to 3 and 3 to 4. So in this case the volume is constant, in this case the heat that is supplied is pressure is constant, and 4 to 5 is the isentropic expansion, and 5 to 1 is the heat rejection process, that is Q2, and here it is Q1, and the volume V3 and V2 is constant, that is V2, and the volume V5 and V1 is also the same, that is V1. So I can write here like this. Okay, let's come to the given data, that what the statement say and what type of data the statement provided us. So the maximum temperature means T4, that is 2000 centigrade. Add 273 with it to convert that into Kelvin, and you will get 2273 Kelvin. And the minimum temperature, that is T1 17 centigrade. Just add 273 with it to convert into Kelvin, it will become 290 Kelvin. The maximum pressure, that is P3. Here the maximum pressure will be at P3, that is also equal to P4, and that is 70 bar, and the minimum pressure that is at P1, that is 1 bar. And what is the compression ratio? So compression ratio is equal to V1 divided by V2, and that is equal to 18. Okay, next, what things we need to calculate, that is the cycle efficiency. So we need to find the cycle efficiency and the mean effective pressure. So we need to find these two things. In order to find these two things, let me write first the formula to find the efficiency, that is equal to work output, so net work output to the heat supplied, and the net work output is equal to heat supplied minus heat rejected divided by heat supplied. So the heat that is supplied is equal to, at this process, 2 to 3 and then 3 to 4, as I already told you. So it will be equal to CV T3 minus T2 plus CP T4 minus T3, and the heat that is rejected, that is equal to Q2, it will be equal to CV T5 minus T1. So in order to calculate the efficiency of the cycle, you must be familiar with the values of the temperature at every point. So the temperature at 1 is given, T5 need to calculate, T3 that is need to be calculated, T4 is already given. So the maximum and minimum temperatures of this cycle is given. All the temperature we need to calculate first to find the efficiency of this cycle. Okay, let's come to the solution. So from process 1 to 2, that is T2 divided by T1, that is equal to V2 divided by V1 divided by V2 into gamma minus 1 So what is V1 by V2? That is 18 into gamma minus 1, that is equal to 0.4. Gamma is 1.4. When you subtract 1 from it, it will become 0.4. So after simplification, you will get T2, that is equal to, what is T1 value? That is 290 multiplied by 18, 0.4 power. Now the T2 value you will get, that is 921.5 Kelvin. So that is the T2 value. Next we need to find the temperatures at T3. So before finding the temperature at T3, you will need to find the pressure at P3. So if you consider here, this is the constant volume heat addition process. There is a direct relationship between temperature and pressure. So I can write that P3 divided by P2, that is equal to T3 divided by T2. So I need to find the temperature T3, so I can write T3 is equal to P3 divided by P2 multiplied by T2. Okay, but the value of P2 is unknown, so first we will find the P2 to find the T3. So P2 divided by P1, that is equal to V1 divided by V2 and equal to power gamma. So it will become 18 into 1.4. So the P2 value will be equal to 18 power 1.4, and what is the P1 value? That is 1 bar, and you will get 57.2 bar. Now simple, put this P2 value in this formula to find the T3 value. So the T3, that is equal to, what is P3? That is maximum 70 divided by 57.2 multiplied by, what is T2? T2 is 921.5. So you will get the T3 value, that is equal to, after the simplification, that is 1127.7 K. So this is T3. So T1 was given, T2 is determined, T3 is also determined now, and T4 is the maximum value that has been given in the statement, and T5 still need to find. So to find the T5 now, we need to find the V5 by V4. Okay, look at this process. At process 3 to 4, this is constant volume. So it's a constant volume heat addition process. So there is direct relationship between volumes and temperature. So I can write that V4 divided by V3, that is equal to T4 divided by T3. So what is T4? That is 2273, and what is T3? That is 1127.7. So after simplifications on calculator, you will get the value, that is 2.015. So you can get the V1 divided by V3 value, that is 2.10. So 2.015. So this value will help you in order to find the V5 by V4 value, and that V5 by V4 value will help you to find the T5 value. Now to find that V5 by V4, just simply in terms of V5 I can write V1 divided by V4. Now multiply and divide V2 with it. So in this value and V2, and in term of V2 is also equal to V3, so I can write it like this: V1 divided by V2 multiply by V3. So in term of V2 I write V3 divided by, this is V3 divided by V4. So the value of V1 by V2, that is 18, and V3 by V4 value, this is V4 by V3. No, this is V4. Remember, because this is default, it must be V4. So this is the value of V4 by V3. So the value of V3 by V4 will be reciprocal of this value, that is 2.015. So 18 divided by 2.015 finally will give you the V5 divided by V4 value, that is 18 divided by 2.015, and it will be equal to 8.933. Now to find the temperatures T4 divided by T5, I can write V5 divided by V4 into gamma minus 1. So here I can write that T4 divided by T5, that is equal to, what is V4 divided by V5? 8.933 to the power, that is 0.4. So the final value of the temperature T5 will be equal to the value of T4 divided by 8.933 into the power 0.4, and the T4 value here it is 273. So divide 273 on calculator by this value, we will get the T4 T5 value. So here that is T5 is equal to 946.6 Kelvin. So this is T5 value. So all the temperature values at every corresponding point has been determined, and some are given, so we can easily calculate the heat that is supplied. So here I can write that the heat that is supplied is equal to Cv into T3 minus T2 plus Cp into T4 minus T3. So the heat that is supplied, I'm just writing in the corresponding value. What is T3? That is 1127.7 minus T2, that is 921.5, and the Cp is 1.005, and T5 that is 2273 minus T3, that is 1127.7. So after simplification you will get the heat that is supplied is equal to that is equal to 1298 kilojoule per kg. So next is the heat that is rejected is equal to Q2, and that is equal to CVT5 minus T1. So what is CV? That is equal to 0.718. T5 value is 946.6 minus 290. So you will get the heat that is rejected, that is equal to, after simplification you will find its value, that is 471.4 kilojoule per kg. Okay. Next, to find the net work output, that is denoted by W, and it will be equal to Q1 minus Q2, and it will be equal to 1298 minus 471.4, and you will get its value, that is almost 826 kilojoule per kg. So the efficiency, that is equal to the net work output divided by heat supplied. So the net work output, that is 826 divided by heat that is supplied, that is 1298, and you will get its value, that is 63.6%. Next is to find the mean effective pressure, and this is the or answer that is provided in the statement to find the efficiency of the cycle. So the efficiency of the cycle has been calculated. Next is to find the mean effective pressures. It will equal to work done divided by the volume that is under the piston, that is equal to V1 minus V2. So we need to find V1, that is equal to R T1 divided by P1. So that R is 287, temperature is 290 divided by P1 is 1 bar 10 to the power 5. Convert that into SI unit, and you will find its value, that is 0.8323 meter cube per kg. Next, the compression ratio that is given, that is equal to V1 divided by V2, and it is equal to 18. So the V2 value will be equal to V1 divided by 18. So 0.8323 divided by 18, and you will find its value, that is equal to 0.04623. We now just put the values of the corresponding terms in this formula to find the mean effective pressure. So the mean effective pressure, that is equal to the work done, that is 826 divided by, so it's in kilojoules, so you multiply 1000 with it also, and divide with the volume, that is V1. V1 is 0.8323 minus 0.04623. So to convert its value into bar, divide it with the 10 to the power 5 to convert that value directly into bar. So the mean effective pressures of this problem statement you will get after simplification of this value, that will be get 10.5 bar. This is the final answer of the this parts of the problem. Thank you so much for watching. More videos on such type of problems and examples are on the way. Stay tuned with us. Thank you.